Hello everyone, I am Dr. Sunita Dole. The topic covered is relational database design, decomposition using functional dependency. There is a formal methodology for evaluating whether a relational schema should be decomposed. This methodology is based on the concept of keys and functional dependencies. Learning outcome. At the end of the session, students will be able to check the functional dependency that hold on the relation and decompose the given relation into BCNF. Decomposition using functional dependencies. Keys and functional dependencies. An instance of a relation that satisfies all real-world constraints is called a legal instance of relation, and a legal instance of a database is one where all the relation instances are legal instances. For example, some of the constraints that are expected to hold in a university database are: students and instructor are uniquely identified by their ID. Each student and instructor has only one name. Each instructor and the student is associated with only one department. Decide whether a particular relation R is in good form. In the case that relation R is not in the good form, decompose it into the set of relations R1, R2 and so on up to Rn such that each relation is in good form and the decomposition is a lossless joint decomposition. Our theory is based on functional dependency and the multivalued dependencies. Let R be a relation schema and alpha, beta are the subset of R, where alpha and beta represent a set of attributes. The functional dependency alpha function determines beta holds on the relation R if and only if for any legal relation whenever any two tuples T1 and T2 of R agrees on the attribute alpha, then they also agree on the attribute beta. That is, T1 of alpha is equal to T2 of alpha implies T1 of beta is equal to T2 of beta. Example, consider relation R with two attributes A and B with the following instance of R. On this instance, attribute A function determines B does not hold, as for A is equal to 1, there are two values of B, that is 4 and 5. But the attribute B function determines A does hold, as for every value of B there is a single value of A. Let R be a relation schema with the 5 attributes A, B, C, D and E. Attribute A function determines B hold on this relation, as the attribute value of A for all tuple in this table is unique. So the attribute A function determines CD and the attribute A function determines BCDE also hold for the same reason. So whenever the left hand side of the functional dependency contains single attribute, that attribute has a unique value for each tuple of the relation, then that functional dependency always hold on the relation. Let R be a relation schema with the 5 attributes A, B, C, D and E. The attribute A function determines C hold on this relation, as the attribute value of C on the right side of the functional dependency for all tuples in this table is same. So the attribute BD function determines C and the attribute ABDE function determines C also hold for the same reason. So whenever right hand side of the functional dependency contains single attribute and that attribute has the same value for each tuple of the relation, then that functional dependency always hold on the relation. Let R be a relation schema with 4 attributes: employee ID, employee name, department ID and department name. Employee ID function determines employee name and the employee ID function determines employee department ID hold on this relation, as the attribute value of employee ID for all tuples in this table is unique. Department ID function determines department name also hold on this relation, as for every value of the department ID there is a single value of department name. K is a super key for the relation schema R if and only if K function determines R. K is a candidate key for relation R if and only if K function determines R and for no alpha proper subset of K, alpha functionally determines R. Functional dependencies also allows us to express the constraint that cannot be expressed using superkeys. Consider the schema: instructor department with the attribute ID, name, salary, department name, building and the budget. We expect these functional dependencies to hold, that is, department name functionally determines building and ID functionally determines building, but would not expect the following to hold, that is, department name functionally determines salary, as particular department may have different salary values. We use the functional dependencies to test the relation to see if they are legal under a set or given set of functional dependencies. If a relation R is legal under a set F of functional dependencies, we say that R satisfies F. We also use the functional dependencies to specify the constraint on the set of legal relation. We say that F holds on R if all legal relation on R satisfy the set of functional dependencies F. A functional dependency of the form alpha functionally determines beta is trivial if beta is a subset of alpha. For example, ID, name functionally determines name, as the name on the right hand side of the functional dependency is a subset of set of attributes on the left hand side of the functional dependency. Similarly, name functionally determines name and the attribute AB functionally determines A are the examples of trivial functional dependency. Otherwise, the functional dependency is non-trivial. For example, attribute AB functionally determines ABC, as the set of attribute ABC is not a subset of set of attributes AB. Similarly, department name functionally determines building. These are the non-trivial functional dependencies. Given a set F of the functional dependencies, there are certain other functional dependencies that are logically implied by F. For example, if A functionally determines B and B functionally determines C, then we can infer that A functionally determines C. The set of all functional dependencies logically implied by F is the closure of F. We denote the closure of F by F raised to plus. So F raised to plus is a superset of F. So if F is equal to A functionally determines B and B functionally determines C, then F raised to plus is equal to A functionally determines B, B functionally determines C and A functionally determines C. BCNF. A relation schema R is in BCNF with respect to a set of functional dependencies if for all functional dependencies in F raised to plus of the form alpha functionally determines beta, where alpha and beta are the subset of R, then at least one of the following holds. First, alpha functionally determines beta is a trivial functional dependency and alpha is a superkey of R. Now consider the example schema which is not in BCNF. So instructor department with the attribute ID, name, salary, department name, building and budget. Because department name functionally determines building and budget holds on the instructor department relation, but department is not a superkey. Suppose we have the schema R and the non-trivial dependency alpha functionally determines beta causes violation of BCNF. We decompose R into alpha union beta and R minus beta minus alpha. So in our example, instructor department with the attribute ID, name, salary, department name, building and budget, alpha is equal to department name and beta is equal to building and the budget. So here in our example, now instructor department is replaced by the two relations, that is department with the department name, building and the budget, and instructor with the ID, name, salary and the department name. Now pause this video and reflect on this question for a minute or 2 minutes and write your response. Once you have written the answer to this question, then you can restart playing this video. Let R be a relation schema with the attribute A, B, C, D and E. Now check the following functional dependencies on above relation. I hope all of you have completed this activity. Let R be a relation schema with the attribute A, B, C, D, E. A functionally determines BC, DE functionally determines C, and BC functionally determines A. But C does not functionally determine DE, as C has three different values of DE, that is 4, 5, 6, 5 and 6, 6 for the same value of C. These are the references used while preparing the presentation. Thank you.